here, a little bit, and then including parts of chapter 5 because this is related to the next lab, lab 4 and 5. What we'll be doing is using rotational motion, part of what we call Newton's laws. So, chapter 4 is related to Newton's laws of motion, right? And these were developed by Isaac Newton in the 1660s, 70s, trying to understand how objects moved, what forces were required to keep them moving, and how they responded to those forces. So, first law is object in motion remains in motion unless external force acts on it. All right, what does this mean? Well, unfortunately, I've seen cases of this is, if you're going a car going down a highway at a high rate of speed, and then suddenly you have to turn, or suddenly there's a turn in front of you, all right? So you're going, say, at 50 meters per second, which is about 110 miles per hour on the road, and suddenly there's a curve here that you see, and you're going too fast for the turn. As we'll get into chapter 5, in part with friction, in parts of chapter 4 with friction, is you're just going constant speed, constant velocity, and then suddenly your turn. Well, if the car is going too fast for the turn, we'll talk about this, Newton's law of first motion, unfortunately, is always waiting to take over, and you'll go straight off the road and either crash, all right? So you have to have some sort of force to keep you in the turn. The second thing is out in space. If something is thrown out in space, say, you just push it out there, it'll just go on forever and ever. If it's away from any gravitational forces, just go on forever and ever. It doesn't require any forces. The idea of forces being required is basically a very old concept. It was thought that because objects on a table, if I push this on my hand slightly, it stops right away. Well, that's because of the frictional forces stopping. If I was to throw it, slight, there's no friction, much like a hockey puck, it'll just go on and on and on until it stops. So if there's no frictional forces, no other forces, no air resistance, it'll just keep going a straight line forever. So if you apply a force to that, that will cause it to accelerate one way or the other, or decelerate, slow it down. And that's what we call Newton's second law. And that's what we give by the formula, force is mass times acceleration, where this is in newtons. We've already used this briefly already. This is in kilograms, and this is in meters per second squared. So that's all Newton's first law is. If we apply a force to something, it will accelerate. If F is 0, then the acceleration is 0 and has constant velocity. Okay. And then finally, Newton's third law is, I'll put it over here, third law is action, reaction. And we can see this if we look in the book. Chapter 4, this picture showing the space shuttle being launched. The rocket engine is sending exhaust out the back. The rest of it goes forward. Now, this exhaust does not push against the ground. What it does is they send it out as fast as possible, up to speeds of 3 kilometers per second, which accelerates it that way. So that's action-reaction. It's like jumping off a boat. You know, you jump off a boat onto the dock, the boat goes backwards, you get on the docks, and then the boat's lost. You know, it was actually one of the problems with space development. There was this thought that spaceships, rockets would only work in the Earth's atmosphere because it was thought that the exhaust pushing out would push against the air, which caused it to propel, so they would not work in space because there's nothing to push against. Well, that's totally wrong. It turns out that issue works better. It's how fast you throw stuff out the back to get the rocket going the other way. So those are Newton's 3 laws of motion. Object in motion remains in motion unless an external force acts on it. Newton's second law, F equals ma. If F is 0, velocity is constant. And third law is action-reaction. You exhaust, throw something this way, you go that way. All right, so that's Newton's third laws of motion. Okay. On first part, we just talked about Newton's 3 laws of motion. I want to get into a little more detail of the second law, F equals ma. All right, now we have basically 2 kinds of acceleration. We've been dealing with so far linear acceleration. So if you're in a car, right, and you accelerate at 10 meters per second squared, right, you know, that's pretty good. That's 1 g-force. You will feel an acceleration, acceleration pulling you backwards into the seat as you accelerate. I mean, this is quite a speed, velocity. If you go that acceleration in time of, say, 5 seconds, all right, your velocity will be, again, acceleration times time. This will be 10 times 5. This would be 50 meters per second, which is about 110 miles per hour. So that's pretty fast. It goes 0 to 110 in 5 seconds is quite the acceleration. All right, you would feel it that way. If you're going at a constant velocity of, say, 50 meters per second, 110 miles per hour, as long as you go in a straight line, you don't feel anything at all. You're going in a straight line, acceleration is 0. So if you go in a straight line at 50 meters per second, so you accelerate, and then at this point, acceleration is 0, you won't feel anything. That's like being in a plane 500 miles per hour. You have a constant speed. You don't feel anything other than you feel like you're on the ground. Now, another case, we talked about this earlier, is moving in a circle or making a hard turn. All right? If you're moving at, say, V is 50 meters per second on a hard turn, we saw this with one of the quizzes, the Indy car race video, where they're driving around on the Indy car 500. All right, if you're looking at your speedometer and you're going 110 miles per hour on a curve, you certainly are not feeling like nothing's happening. You're feeling like you're being thrown outwards. Right. This feeling of being thrown outwards is what we call centrifugal acceleration, because the car is forcing you inwards, but you want to go outward. You want to go straight. every single moment. So this is related to what we call then centripetal acceleration. And this is related, same kind of acceleration that you are linear, but it's calculated differently. The centripetal acceleration, AC, depends on your velocity, square, the speed squared, divided by the radius of curvature of your turn or circle. So this would be R, and say R is 50 meters, and we're going at 50 meters per second. What would be your acceleration? This would be 50 squared divided by 50. That would be 50 meters per second squared, which is roughly 5g. That would be a very hard turn. I mean, 50 meters is not very wide. And to take it at that speed would be very hard. So if you have any slickness on the road, you go flying off. So that's centripetal acceleration. It depends on the speed and raised curvature. So this is actually part of chapter 5A, because this is related to the lab 4 and 5 as far as that's concerned. So both of these are related to Newton's first law of second law of motion, but in this case we have linear acceleration. In this case we have what we call centripetal acceleration, moving at a constant speed in a circle. So that is chapter 5, the beginning part there. Again, on this chapter, we'll be kind of mixing, going back and forth, because you have Newton's law of motion involved both of those. We also have the concept of friction, right? Because friction is what keeps you on the road in the first place when you're trying to make a hard turn. So that'll be the next lecture. We'll be related.